Who wants to name some of the key assumptions of an ideal gas? Like I said, to make the math easy and sort of to set us up, we'll do ideal gases before we move into more sophisticated molecules. So what are there's three that are going to come up on this slide. Yes?
Perfectly elastic collisions.
Perfectly elastic collisions. What else? I said this one earlier. The particles aren't occupying space. We treat them like they have no volume. In addition to perfectly elastic collisions with, say, the wall of the vessel they're in, or with each other, do they have any bonds in them? They don't have bonds, or if they do, we ignore what that might mean in terms of potential energy, okay? We don't think of any intermolecular forces between them. They're not interacting with each other. They're not interacting with the wall. All of their collisions are perfectly elastic. All the kinetic energy going in is all the kinetic energy bouncing back off. Those are the assumptions we're making, okay? And again, it makes things manageable for us. So if I have an ideal gas in a container and I apply a heat source, where does the heat go? What's going to happen to the ideal gas? I don't let it expand. Now what else could happen? Pretend it's a fixed container. I'm hearing it mumbled. Temperature is going to go up. And what is temperature a measure of? Kinetic energy. Okay? In an ideal gas in a fixed square, and I put in heat, my little arrows here indicating velocity get bigger. Okay? The only thing that can happen is an increase in kinetic energy. So the only thing that would happen then, we'd see a measurable increase in temperature. But as soon as I have a more sophisticated molecule, heat will go into two things. One, it will increase the speed that these things are moving around at. So the kinetic energy will go up. But what I also can then have is changes to the potential energy. And so if we treat this as maybe, say, like a cis bond in the backbone of whatever this is, or I'm sorry, a trans conformation, the cis conformation is of higher energy, but that could be one of the things that the heat goes into doing. Okay? It can go into rotating the bonds, vibrating the bonds, getting into previously impossible conformations, right? So it's not going to just go into kinetic energy anymore the way the ideal gas is behaving. The ideal gas behaves something called the ideal gas law. Who knows what the ideal gas law is? Who wants to say it to me? PV equals nRT. It's beautiful. It obeys this equation. What is the P? What is the V? What is the N? What is the N? Number of moles of the gas. T is? T is temperature. And the R is the gas constant. And who invented the gas constant? I don't know either. I forgot. Who cares? Okay. It's the universal gas constant. But what is it for? Why is it there? What does it do? To make it make sense. That's really the answer. It's a proportionality constant, so you can relate these relatively different scales of temperature, volume, and pressure, and moles of gas. But it also then makes all the units work out pretty, right? It's a way to relate these things. And I don't remember who invented it. It's a combo of people. But what we will find is it is related to Boltzmann's constant, which we'll be using soon. Okay, they're very related. You will always be given this. Okay, you don't have to memorize it. You may memorize it just by using it several times in this class. So these are the two versions that you might see. I generally don't fixate on doing stuff like this too much, asking you to convert between liter atmospheres and joules and things like that, but occasionally I will, so just pay attention. It's always small points off for units, but they add up, right? Okay. Temp was our average kinetic energy, definition of internal energy. Do ideal gases have potential energy? I'm seeing some no's. No, I just said this. We're assuming no. We're treating them like there's no bond storing energy and their collisions are perfect. Treat potential energy as 0. So then what is the internal energy of an ideal gas given by? Just kinetic energy. And this is the definition of kinetic energy for an ideal gas. 3 halves nRT. The proof is box 6.3 in your book, and this Khan Academy video, which is not super long, is very good talking about this. I can't do the proof for this in terms of time, okay? If you wanna prove to yourself that the definition of kinetic energy for an ideal gas is equal to 3 halves nRT, these are the resources I recommend, okay? Because I know some people aren't comfortable just using what I say to use, and some people are, okay? So that means that when we're talking about an ideal gas, we're only talking about changes of kinetic energy, and it's a function exclusively of temperature. This is a constant, 1.5. Number of moles is going to be a constant in all of our storylines. We're not going to be adding more, taking out of the balloon that's filling up or whatever is happening, right? So the number of moles will be constant, gas constant's a constant. So when we talk about changes in internal energy or U, we'll be really only talking about what's going on with temp. So if I tell you it's an isothermal case, you can just set it equal to 0. Delta T isn't changing. Delta U won't be changing either, okay? But this is for ideal gas case, and this will be after the quiz. I don't know how many slides I have to say the same thing. So I will recommend sometimes keeping subscripts on helps you keep things oriented. Sometimes subscripts like system and surroundings so that you know what you're talking about. Carry those through your math. Might help you keep things from getting screwed up, especially science, okay? So internal energy of an ideal gas is just its kinetic energy. It is a function dependent only on a change in temperature, okay? So this big delta here is of course telling us we have change in. I'm talking about measurable temp and internal energy at typically time will be our 2 different points, but maybe something else, time's always involved, and some other totally different point or condition, right? And I can subtract them. One of the things that we will see coming up is differential form. So sort of the lowercase d, is infinitesimal changes in internal energy or infinitesimal changes in temperature, okay? Those are, I cannot subtract them, I have to integrate, okay? So get ready to see both forms sort of all the time whenever I want to use whichever one I want to use. Okay. Units, just kind of always a mental check for yourself. Do my units make sense, okay? So ideal gas, the units on this, I have joules per mole Kelvin is my units for R. Temp is going to be Kelvin, so the kelvins would drop out. I could multiply through by moles, however many moles I have, and then get just joules, or I could go per mole if I want, either way. And joules or joules per mole is an appropriate unit for internal energy, so I feel happy.